In the south of France, 35 nations are currently assembling one of the most complex machines ever designed. It's called ITER, and its sprawling footprint represents a global commitment to replicate the power source of the stars on Earth. In the United States, private ventures like Commonwealth Fusion Systems and Helion are matching that momentum. They are aggressively accelerating the timeline for commercial reactors, aiming to deliver fusion power to the grid within our lifetimes. The goal is nuclear fusion. Inside these machines, hydrogen gas is heated to tens of millions of degrees, forcing atoms to collide and ignite into a swirling ring of superheated plasma that releases massive amounts of energy. A working fusion reactor provides a source of energy that is effectively infinite. Mastering this reaction is the specific physical requirement for our species to leave its planetary cradle and survive across geological timescales. Astrophysicist Nikolai Kardashev proposed an objective way to measure the technological advancement of any civilization in the universe. His scale ignores politics and geography, ranking a species entirely on its total energy consumption. On this metric, humanity currently stands at 0.73. To reach a full Type 1 civilization, a species must harness 100% of its home planet's energy. Sustained commercial fusion allows us to lock into place at that level. But even a fully optimized Earth has strict physical limits. A planetary energy budget is finite. Eventually, a growing, expanding civilization will consume every watt its home world has to offer. To avoid stagnation, that civilization must look outward. The only viable path forward is to graduate to Type 2 status by capturing the raw thermonuclear output of the solar system's host star. Harvesting an entire star requires material. A Type 2 civilization would need to dismantle dead planets and asteroids, forging that raw matter into millions of solar collectors to completely enclose their sun. Collecting power is only the first step. An advanced species might reconfigure that swarm into a matryoshka brain, a structure designed purely for computing. This chart shows how the thermodynamic engine operates. The innermost shell captures the star's energy, runs its computations at extreme temperatures, and radiates waste heat outward. Then, the cooler shell takes over, recycling that heat for its own calculations before venting further out. By stacking these shells across millions of miles, the structure extracts every usable drop of energy, generating a staggering processing capacity. With the computing power of 1 trillion Earths, a civilization could simulate billions of parallel universes, or even upload the consciousness of their entire species into a permanent digital reality. Sometimes computational power isn't enough. Our galaxy is a hazardous environment, and a stray rogue star or a nearby supernova could sterilize a solar system from dozens of light years away. To survive, you have to move the entire solar system. The Shkadov thruster is a gargantuan passive mirror designed to hover above a star and function as a cosmic engine. Light carries physical momentum. When photons stream out of the star, they hit this megastructure and bounce back. Reflecting half of the star's immense light output in a single direction creates a directional thrust, pushing the star away from the mirror. It requires zero active fuel, relying entirely on the star's own radiation. The acceleration is slight, but over 1 billion years, this pressure could push our sun across the Milky Way. Because these megastructures rely on the strict laws of thermodynamics and gravity, they would leave massive physical footprints in the observable universe. Astronomers hunt for exoplanets by watching for microscopic dimming in a star's light. To detect these transits, we rely on satellites shielded in high-grade hardware, like the copper casing shown here, to capture the data. This graph illustrates a normal planetary transit, a smooth, symmetrical U-shaped dip as a round planet crosses the star. But a colossal curved mirror like a Shkadov thruster would register as an abrupt, jagged drop, creating a highly asymmetrical light signature. In 2015, astronomers looking at KIC 8462852 noticed exactly this kind of chaotic, unexplained dimming. While later data suggested clouds of space dust, the initial shock triggered a serious investigation into detecting alien megastructures. We now possess the astrophysical tools to hunt for new markers, the physical signs of a Type 2 civilization operating right now in the Milky Way. The forces governing these massive alien engines are the exact same physical laws we are currently manipulating in terrestrial laboratories. The engineers at ITER and in private fusion labs are manipulating the same plasma dynamics that will one day sustain human life across the stars. Their work provides the physical foundation for our long-term survival. Building an artificial sun on Earth is the first necessary step on the Kardashev scale. If we can master the physics of fusion today, our descendants may one day engineer the stars themselves.